Good morning, everybody, and welcome to today's Ohio Rock Talks, last one of this Earth Science Week. And today we're going to talk about the everyday uses for geological maps. And this team here has put together something that I think most of us can probably relate to. So I'm going to introduce you first. We have Tyler Norris, Erica Danielson, Brittany Perrick, Tom Valikovics, and we're going to start here with Andy Nash. And Chuck here is going to help with the Q&A. I'm Stephanie, and throw your questions in there. We'll get them answered as they come, and we'll save some time at the end as well for you to ask questions. So, Andy, go ahead.
Great. I'm going to go ahead and start sharing this PowerPoint. Hopefully everybody can get it now. All right. So welcome everybody to our latest installment of Ohio Rocks Talks. Today we're going to be talking about everyday uses for geologic maps.
Hey, Andy.
And this is the last in our installment of Earth Science Week 2020 webinars.
Andy, I'm going to interrupt you real quick. I'm not seeing your PowerPoint to pull up here.
Oh, really? How's that?
There we go. Thank you.
Okay.
Sorry.
Yeah, no problem. So, like I said, this is the last in our series for Earth Science Week. We're going to be talking about these everyday uses for geologic maps. And if you've missed any of our previous webinars, I think there's a link right now in the Q&A that you can click on eventually. They'll be uploaded to YouTube, probably not just yet, but look for them in the coming weeks. And so we probably use maps every day, all of us, without really even thinking about it. We just kind of take them for granted. And geologic maps are kind of the same way for most people. But today, hopefully, you can get more of an appreciation for geologic maps as we learn more about them. So, like I said, most people probably use maps every day. If you need to get from point A to point B and you don't know exactly how to get there, say you want to navigate to a state park to enjoy some of this beautiful fall weather, you're probably going to pull up a map on your phone or on the internet and type in some addresses and get the best route and figure out the best way to get there, even through traffic. Once you get to the park, maybe you need to know, is it going to be rainy all day? Or is it going to be sunny, beautiful day to enjoy the fall colors? So you might pull up a weather map online to look for that too. And then at the park, maybe you're looking for a strenuous hike and you want a high slope area, or you want a flat hike and you want to look for kind of a flatter area. Maybe you'll use a topographic map available to figure out what the terrain is like when you're there. Or maybe you want to hike near a river, so you'll pull up a topographic map. And then maybe something that other people can relate to is home buying. If you want to find a new place to live or move houses or anything like that, maybe you pull up a map to look at all the available houses in the city that you're interested in. And this will be something that we kind of talk about later as we get into how geologic maps can relate to some of these maps that we use every day and kind of take for granted. But first, I wanted to talk a little bit about some of the elements that build maps, or that we can build maps with. These are kind of the accessories to maps. Like, we think of maps as being that location data, but there are other components that we need to put into them so that readers can easily understand or read the map. And that first one is the title. So we've got a map here of the United States of America, and once you know it, there's a nice big bold title right here that says the United States of America. And so you can see that right there. But then we've got this map with all these colors, and we don't necessarily know exactly what those colors mean or if they mean anything at all. So there's more elements that we can put into the map to make it even better. So one of those other elements are north arrows, or cardinal directions. So you can see we've got compass rose here. We've got north, east, south, and west labeled. Most maps, that north arrow is going to be pointed up. North will be up on maps most of the time. But that's not always true. Sometimes the north arrow, like this one here, is rotated for various reasons. So you just want to make sure you know which direction north is if you need to navigate around a map. And then sometimes there's some complicated north arrows. And so this one right here is kind of a common north arrow that you'll find on topographic maps that we talked about earlier. And so there's this concept between true north and magnetic north. So as we think about true north, that's like the North Pole where Santa lives, right? And so you've got the top of the globe, that's kind of the true north. And so that's marked by this star. but there's this magnetic field that surrounds Earth, and it shifts a little bit where the north magnetic pole is. And so we have to rotate or adjust compasses. If you're going to use a compass and a map to navigate around, you need to adjust that compass to adjust for magnetic north, because remember that compass needle is going to point to magnetic north and not true north. And the next map element we want to talk about is scale. And this is a really important one because all kinds of maps can have different scales. And so we can express scale in two ways, really. There's scale text and then there's scale bars. And scale text can actually be broken down into two categories of its own. You can talk about relative scale. So in this example, 1 to 24,000. Well, what does that mean? There's not really any units on there, and that's because you can use any units. It's relative. So we can say that 1 inch on the map equals 24,000 inches in real life. So essentially when we're making a map, we're taking 24,000, or substitute whatever number for whatever scale it is, inches, and shrinking it down all the way to 1 inch on the map. And so that's what scale is. And then there's absolute scale, where you've got 1 inch equals 2,000 feet, or 1 inch equals 0.38 miles. These are kind of absolute values that you can use to calculate distance on a map. And scale bars are really nice for looking at kind of a visual distance. If you want to measure with a ruler, just kind of measure by your eye on the map. They give you a good idea of the distance it would take in real life to move across the map. And the last element that I wanted to talk about was the legend. And so this is a map of Old Man's Cave Campground. It's a great time to go camp in Hocking Hills, and so you can rent any of these sites. But this legend here tells you all about what is shown on this map. If we didn't have this legend, if you pretended this wasn't here, what would all these symbols mean? They'd be hard to figure out. And so the legend tells you what these symbols actually mean. So for example, we've got this little house looking thing here. Who would know what that is without looking at the legend? And it's camper cabins. You know, you might see a phone over here, and that's pretty obvious, like there's a telephone. But look at this symbol. I mean, what is that? Is there Wi-Fi here at this camp? No, it's an amphitheater. So you can use the legend to really express information really easily through a map. And then notice there's some other elements that we've talked about before. Look at this north arrow. See how it's rotated? So north is actually in this direction. And the reason the map authors wanted to rotate this map was so that it could fit on one sheet of paper. You can see that if it was north was pointed up, the campground would be a little bit wonky and it wouldn't fit on one 8.5 by 11 sheet of paper. So sometimes that's a really good reason for moving north around is for layout, as we would say. And then also, like I mentioned earlier, there's a title down here that tells you right away, I'm looking at Old Man's Cave Campground and not, you know, John Bryan State Park. So these are a great use of elements in all these different maps. But then what we think about with a geologic map, you know, they're a lot like those other maps because they use those same elements. But geologic maps are going to show the distribution of rocks, minerals, sediments, and all kinds of other natural features. And there are a variety of different kinds of geologic maps. Some show kind of all those things all in one. Some are really focused on just one of those things like rocks or just minerals. But you can see an example here that we're probably most known for at the Ohio Geological Survey is this bedrock map of Ohio. So this is kind of the bedrock that makes up all of our state. And you can see we'll talk about that a little bit later, but that's kind of the basic of what a geologic map is. But now we kind of get into kind of the nuts and bolts of geologic mapping when we think about applying it to a real world issue. And so here I've got this topographic map, which I've talked a little bit about earlier topographic maps, but I'll explain. So these lines right here are called contours, and they tell you the elevation of the land surface. So if you were to walk along this contour, you'd be walking at 500 feet above sea level. So you wouldn't be going up or down in elevation if you walked along the line. But if you walked between the lines, you'd be changing elevation. So if you were to walk from here to here, you would go up in 50 feet in elevation because this contour interval is 50 feet. And so you can start to see what the land surface looks like by looking at a topographic map. And so this is my property here and a topographic map of it. And you can see that in the south, there's this big hill because we go from 500 to 700 feet, this big round hill. And then we've got this river that cuts right through the middle. And you've got contour lines right here, 400 and 450. So the river is moving in this direction. One little tip on topographic maps is that these and the contour lines are going to point upstream. So you can see if you move from 400 to 450 feet. But that's basically all I really know from this map, is that there's a little bit of a hill here, a hill in the south, and then a river through the middle. And then I've got this area, which I can use my legend to say that, oh, this is definitely a wetland. And I've got a little pond over here too. But that's kind of all I know about my property. And my issue is I really want to build a house here, but I don't really know the best place to build a house. So I'm going to have to ask for some help from my friends at the Ohio Geological Survey. Maybe they can provide some geologic maps for me to tell me the best place to build this house. So why don't I throw it over to Tyler and see what kind of maps he has for me.
Awesome. So thanks, Andy, and I'd be happy to help with your investigation into the property. So let's just talk about the surface of the land. So superficial geology can be complex and includes loose sediment and soils from the ground. And in some places like Ohio, soft sediment was also deposited by glaciers. So depending on the land's shape and what the material of the ground is made up of, we can figure out why the land looks the way it does today. But for building a house, I can think of at least two maps that I have that might be able to help you out with. And we'll be taking this general topographic map that you have made here, and we'll begin adding different types of geologic elements to it. And then we can slowly begin developing the full picture of your property. So for example, we're looking at just superficial geology. Those marsh symbols to the west leads me to believe that there are some organics piled up from this poorly drained soils that are near that stream. So first, let's look at how thick the sediments are in your area and how it relates to the shape of the land. And to help us, we'll look at what's called a drift thickness map. So drift thickness map is made up of this drift, and drift is this general name given for the soft, loose sediment that the glaciers left behind after they melted away from the region. However, since there's other types of loose surface materials, things that cover bedrock like alluvium is also included. And this alluvium is a soft sediment and rock that's carried from water, usually by streams, more modern streams. And also a view of what this drift could look like underground is shown on the diagram to the left. So you can see that soft sediment depths and these hard bedrock layers can be deceiving based on just what we can see above the ground. And it's important to know these thicknesses if you plan on building or digging or working on underground structures. And then on the right, you may have noticed there's a drift thickness map for Ohio. And this shows how thick the drift is, mostly where the glaciers once occupied the land, which is about 2/3 of the whole state. And we also show some sediment within the alluvium valleys in the other portions of the state. So looking at the legend, this map tells us that the purples and the bluish colored areas are very thick with drift. So that would mean that'd be very deep until we hit some solid bedrock. And the white southeastern portion of the state is comparatively thin. It doesn't have as much drift covering it because the glaciers didn't quite reach that area. So it's mostly just the solid bedrock exposed, or maybe covered with a thin soil. So we can take a similar drift thickness map for your plot of land. And we can see that the northwest corner of your property is pretty thick with drift. So there's around 60 feet thick of drift that makes up that hill. There's also some loose sediment along the stream. And we also have an area that has thicker sediments near the western edge of the river that might be related to those wetland marsh symbols I told you about before. So remember, these thicknesses are a little different than the surface elevations, which are represented by those contour lines shown on the map already. And we'll get into that in a few moments. But let's find out why that northwest corner of the map is so thick and see what makes up that drift. And we can see what makes up that drift by looking at a superficial geology or a glacial geology map. And there are many different types of superficial geological maps with different information levels of detail, but superficial geology maps show what type of materials the land is made up of and how they relate to different landforms. I think the next slide should show you the glacial geologic map of Ohio with a, let's see, were you advancing the slide yet? Yep, here we go. With different types of landforms that are in Ohio. And the left kind of shows you what the glacial map of Ohio might look like zoomed in if we look at some of those units in a little bit more detail. And all these different units are drawn out and they're given different names based on, and labels based on attributes like their age, their composition, and all that ties into the general landform type feature. And at the Ohio Geological Survey, we also create an interesting surficial geology map called a stack map. And that kind of combines the drift thickness map that I showed you before and some of these surficial units and some things that we can see in the subsurface and then get assigned thicknesses to each of them until we hit some solid bedrock. And that'll help us map out different types of surface materials. So let's see how the surficial geology can relate to your plot of land. So for your property, the next slide will show you that I found that the northwest corner where that drift is very thick is made up of a material called glacial till. And glacial till is this mixture of different sizes of pieces of sediment. So till can be made up of extremely small sediment bits like clay, and maybe even slightly bigger pieces like grains of sand you could find on a beach, or even as big as boulders of these other huge rocks that the glaciers carried with it. So till can sometimes have these solid pieces of rock in it, but it's usually much softer than the solid bedrock that lies underneath it overall. So this till material on your property composes a landform called an end moraine. So it's kind of like a ridge-like feature that shows when the glacier's maximum advance hit at that area, at that exact location. And this till material was then deposited by the glacial ice once it stopped advancing. So the glacial ice then just melted and all that loose sediment that was trapped in the ice was dumped and remained here, and that makes up this hill of till. But there are also other notable areas within that till, like those lenses of sand inside the till. So you can see that by the orange spots on the map to the north. And the glaciers must have deposited some type of concentration of sand as well. So that was partly carried by some meltwater a little bit that the glaciers were kind of discharging while the ice was melting. But we also see other sediments along the river, which is made up that alluvium that I was talking about before. And you also have that swampy bog type area along the river to the west. So now we know that it's notably thick with about 10 feet of sediment, and it's probably mud and organics mixed in there. And all these surficial materials are overlaid by underlaid by the solid bedrock. So we can draw a line across your property from hill to hill. So do that from A to A prime, and I'll help you understand kind of what the general subsurface is going to look like with some of this information. And we can do that by viewing it inside the ground like that drift thickness diagram I showed you before. So you can just imagine just cutting through the earth, like slicing a piece of cake right along that line from starting at A to the northwest and all the way down to A prime in the southeast. So the next slide is going to show you kind of what it looks like along this line. So the next slide will show this, what the cake looks like, you can say, or the land that's underneath your property. What it looks like kind of viewing from the side. So this is known as a cross section because it's what shows you what the section of land looks like across a line. And you can see the surface of the solid bedrock underneath this soft drift. And you can start to get a picture of the geology of the land by combining the drift thickness and the types of materials that we see that make up the drift. So now we know the hill to the right of the section, or the south area on the topographic surficial geology reference map, has no surficial material on it, so it's likely just made up of bedrock. So now we can bring all this together and talk about why all this surficial geology is important, especially relating to your plot of land. So the next slide, we'll compare these two different maps that I have and review all the information and help you decide maybe where you can build a house. So the area that is swampy is a place that I would avoid. So I'll place a big old X over that. Because this house might, if you build something here, there's a possibility that it would be constantly damp because of the soils that are not very well drained. And although it might be soft to dig, you'd probably have to establish some extra drainage around the foundation. But there might be some interesting wildlife on your property because wetlands are usually a pretty biodiverse ecosystem nearby. So if you're interested in enjoying nature, you could maybe build an overlook somewhere nearby. But another area I'd avoid would be building too close to the river. So I put some X's across the river here, just it's kind of obvious, but there's a slight floodplain, and you might run the risk of being flooded during some of these heavy rains if you build there, because flooding risk is a pretty common and often overlooked factor to consider when building. High and dry is generally safer if you have the option. So based on the superficial geology, I would recommend at least perhaps the northwestern region close to the glacial till, because not only would that give you it would be easier to build a foundation, the softer material, but the mixture of sediments might give you a good opportunity for other things, like building a nice garden, so growing a nice garden in the mixed soils. And maybe even the sandier lenses are thick enough and large enough to use like a pit to borrow sand from. And you could use that in other places in your property as well. But there are other locations away from the river, like the interesting hill to the south. And all these areas that are not really colored in or just bedrock. So you have to look at a different geologic map, a bedrock map, to see what that area is made up of. And it might be even better than that hill that I mentioned to the northwest. So to learn more about all this, let's ask our bedrock expert, Erica, to see if she has any maps that can help us out even more. So Erica, I'll pass off all my superficial information and maps, and you can use those as you look into the property's bedrock geology. So take it away, Erica.
Awesome, thanks Tyler, and hey everybody, and hey Andy. So I agree with Tyler, you're definitely going to want to look at a bedrock map, but before we do that, I'm just going to talk a little bit about what bedrock is and why bedrock maps can be so important. So the first diagram we have on this slide is the one similar to the one Tyler was showing you. So we have our drift in green, all that loose, unconsolidated surface sediment, with the bedrock shown underneath that in gray. So the loose unconsolidated sediment doesn't always cover the bedrock. We also have exposures. And so our bedrock is our hard, solid, consolidated rock. It's always going to underlie that sediment. But like I said, if you click Andy in that upper corner of the diagram, it can be exposed at the surface as well, which will look something like a cliff, or like when you're driving down the highway, if you see a big rock wall, that's a bedrock exposure, or what geologists frequently call outcrops. So a bedrock map will not tell you whether or not the bedrock is exposed, because a bedrock map shows you the type of rock closest to the surface of the earth. So we're just going to take a look at our bedrock map on this slide for a little bit. Now, this map is a simplified bedrock map of Ohio, and the colors represent the geologic time period that the rocks formed in. So if we look at our legend, that mentions those are all names of different geologic time periods. They all occurred during the Paleozoic over hundreds of millions of years ago. And let's just take a look at one as an example. So we're going to look at the orange legend right there, and that says Devonian. So if we look at our map, all the orange shaded regions, if we went to any of those locations and saw a rock outcrop, this map is telling us that those rocks would have formed during the Devonian period, which occurred about 420 million years ago to about 358 million years ago. So it spanned tens of millions of years and occurred hundreds of millions of years ago, but we can see those rocks in Ohio today. So if we go to our next slide, I'd like to zoom in on to show you some more detailed bedrock maps. So on our simplified map, I have Delaware County highlighted. And on the simplified map, we see 4 different bedrock units, 4 different colors. But when we zoom in and we look at that more detailed bedrock map of Delaware County, we see about 8 different colors, and they also have unique letter combinations assigned to them. So you can see much more already. But let's go to our next slide and bring up all those different map elements Andy was talking about that we would see on a bedrock map. So we have our title, our north arrow, and our scale bar. And then we also have our legend. And in this case, it's called the description of map units. So I know this is going to be really small. You don't have to read those descriptions right now, but I wanted to put the description for all of these units on this slide so you can see how much information you can really get from looking at a more detailed bedrock map. And without even reading the descriptions, this description of map units is going to tell us some pretty interesting information, because the rock unit that's on the bottom of that description is always going to be the oldest. And then as you move up the description, the youngest rock unit is going to be labeled at the top. So for example, the rock unit that's at the bottom of this description is the one labeled SS in very light green, and that's found on the western side of Delaware County. And the rock unit all the way at the top of the description of map units is labeled MLC, and that's the light blue, and that's found in eastern Delaware County. So if you were to drive from west to east across Delaware County, you'd be moving through progressively younger rocks as you drive across the county. So it's really neat things Bedrock Maps can show you right away without even getting into the details. But let's look at one of these detailed descriptions. And so let's go to our next slide, and we're just going to blow one of these up just as an example. So we're going to look at the rock unit labeled DD, that's dark orange. And there are three main pieces of information that the description is going to tell you right away. So the first piece of information, if you click Andy, is going to be the name. So this unit is called the Delaware Limestone. And the next piece of information you'll see is the age. So this is Middle Devonian. So the Delaware Limestone formed during the Middle Devonian period. And then the next piece of information is the rock type. And so it's a limestone. So I know in this case it sounds redundant, the Delaware limestone is a limestone, but you won't always have the rock type in the name of the unit. And sometimes one rock unit could have several rock types. So you're always going to see that there in the description. Now, following those three pieces of information, you're going to have more details about that rock type. So you'll have, it'll mention details like the color, maybe what the unit looks like in outcrop. It'll mention notes about the mineralogy of the rocks and what unique features can you find in that rock that will distinguish it from the other rock units on the map. So you might be wondering, why do we want to know this information? What is this used for? And there are tons of uses for bedrock maps, but I'm just going to highlight a couple that I guess I find particularly interesting. So maybe you're going out to a state park and you find a really cool fossil while you're there, or maybe you saw some beautiful rocky cliffs and you're just really curious, how did those rocks get there? What type of rocks are they? How old are these fossils I'm seeing? And so a bedrock map is a great place for you to start. If you can locate that state park on a bedrock map, you can look up that information quite easily, and it's a really great jumping off point if you'd like to do more research into the Earth history and the geologic history to learn more about that environment you're seeing. It's also a great tool for people who like fossil and mineral collecting. If you're interested in a certain type of mineral or a fossil of a certain age, you can find those locations on a bedrock map and then make sure you can start there for as you're looking to collect. And then if we think about mineral collecting on a really large scale, we can think about the mining industry. And bedrock maps are really important in the mining industry because they have to know where the rocks are that they're looking to mine. So for example, if if a company is looking to dig a limestone quarry, they have to know where the limestone is. So they'd be interested in looking at that rock type and those details on bedrock maps. And another use for bedrock maps, which I think you could relate to, Andy, is for construction or something like city and land use planning. So before you start any kind of construction project, you really have to understand the geology that you're building on or into. And so the important piece of information in this situation would be the rock type. And so this is because different rock types have unique engineering properties. So these properties, these are properties that impact how you're going to build your structure. So different rock types have different hardness and strength. They weather and break down differently, and this will impact the stability of the structure being built and how it's built. So for example, Andy, if you're interested in digging a foundation for your house, the rock type will affect how easy or difficult it is to dig into the ground. It will affect what equipment you have to use to dig that foundation and how much time it's going to take for you to do that. So let's go to our next slide and we can start looking at the bedrock map of your property. So I looked at our more detailed bedrock map and I just pulled out that rock type information for you, Andy. And you have 4 different rock types on your property. There are 4 different bedrock units. So the oldest one we're going to call Shale 1. And that's in the eastern part of your property. So it's your oldest shale unit. And overlying that is a limestone. So that covers most of your property. And then in that hill to the south, the lower part of that hill is a different shale unit. So we're just going to call that Shale 2. And then overlying that, you have a sandstone. So if you remember before we were saying these topographic lines represent the elevation of the land surface, not the elevation of the bedrock surface. So what we're going to have to do is look at those surficial maps that Tyler was talking about and compare those to the bedrock maps to see where we have exposed bedrock. So we go to our next slide, Andy. We're just going to bring up those SURFICIAL map and that cross section that Tyler was talking about. This is a reminder. And it was helpful because Tyler already labeled where we should have exposed bedrock on these diagrams. So all the white space on these diagrams will be bedrock. So if we just bring up that bedrock map again, we can now use this bedrock map to fill in those blank spaces. So we're going to go to our next slide. And this is what our combined SURFICIAL and bedrock map and cross section look like. So we're going to cover up those SURFICIAL units because Tyler already spoke about those. So if you just click once, Andy. And we're going to talk about now the exposed bedrock. And it looks like you have all 4 bedrock units exposed on your property, Andy. So if you're interested in building in these areas, first I would say you can certainly build on any of them. But like I was saying before, those engineering properties, the rock type is going to affect how hard it might be to dig a basement, for instance, if you're trying to dig a foundation. So let's look at this shale 1 unit. So I'm going to put check marks here because it's probably going to be the easiest rock unit to dig into. It's a really soft shale, weathers pretty easily at the surface, so it will probably be the least labor intensive. Now, if you click again, we're going to talk about the limestone and the sandstone. So these X's aren't here. You're allowed to build on here. You can absolutely build on limestone or sandstone, but it's going to be much more difficult. They're much harder rocks. So it'll probably be a lot more labor intensive and a lot more time to actually dig a foundation in an area like that. And so our last rock unit we're going to look at is that shale 2. And I put question marks here, not because of the rock type or the engineering properties. Those would be pretty similar to shale 1, but because I noticed that this topographic map, the shale is located on a pretty steep slope. Looks like a pretty steep hill. So shale can be fairly unstable in steep slopes. Really any rocks can be. So I don't know if it's really a good idea for you to build in that location. So I'm going to recommend that you speak with another one of our geologists, Brittany, who is an expert in geologic hazard mapping. So we can pass along to Brittany. Thanks.
All right, thank you, Erica. Yeah, it's a good thing you're passing me. Andy, I'm definitely very interested in helping you out with your property, finding out where you can build a proper home. And it's good that you mentioned geohazards because it's something that can affect pretty much anywhere, just depending on what kind of bedrock you're in. And in Ohio, we only have really 3 to worry about, but geohazards can encompass any kind of risk that comes from geologic processes. So volcanoes or huge earthquakes and tsunamis that come from them are all big concerns, but not for here. We don't have to worry about those. We do have 3 that I could be a little more concerned about in this area. We have sinkholes and karst terrain. Then we also have landslides, and then AUMs, which are abandoned underground mine subsidence. So these 3 different things, I'm going to take a look at your property and see what they look like. Now, for these geohazards, we map them a little bit differently than we would do for the SURFICIAL map or the bedrock map. We use a data set called LIDAR, which is produced when a plane flies over the state, shoots a laser at the ground, and then the amount of time it takes for that laser to return to the plane is then used to create a data set, a bunch of points of the elevation of the state. The LIDAR stands for light detection and ranging. That's the laser. And this data set is actually produced by the Ohio Geographically Referenced Information Program. And then we take that LIDAR data and then convert it into a raster or an image data set that we then use as a digital elevation model of the state. So there's the DEM of the state of Ohio, and then we use this to map the different points of geohazards on it. So if we go back to the bedrock map of the NASH property, all geohazards are bedrock dependent. So since we have a couple different ones here, I'm going to designate 2 that I think I should be the most concerned about. I did check. We have a Mines interactive map online, and then also on Erica's bedrock map and Tyler's SURFICIAL map, there was no reference to any sort of mining activity. And nothing on the interactive map either for your location, so we can probably safely rule out any sort of AUM subsidence for this location, which is good. So that means we just have to focus on sinkholes and karst and landslides. So karst forms in carbonate rocks, and since you have a limestone that takes up most of your property, I'm going to be very interested to see if you could have some sinkholes there, and it's a definite possibility. And then also with landslides, they happen, you know, on steeper terrain when there's just been some sort of failure down slope, and then the material can slide down. So Erica was right to be concerned about that particular issue on that southern hill. So if you bring up the DEM for your property, there's a couple of things that jump out to me right away. So you see there are, well, first let me point out my legend for you. The 700-foot line is in the red. That means that's the higher elevation. And then the 400 feet, which is the lower elevation, is going to be the blue. So that means a couple of things. You can see that pond over on the western side in the marshy area kind of goes from that greenish, and it changes elevation to a deeper elevation slightly because it's not a very deep pond. And because of this, I'm going to point out the two depressions that we have that are in the center of the map and then also in the northeastern corner. So these things stand out to me right away for a couple of reasons. They are enclosed, so that means that they are some kind of depression on their own, and they don't have any water in them, so that means that they're well draining. To me, that coupled with that they are on limestone terrain means that they most likely are sinkholes. So if you go to the next slide, I actually checked our online Karst interactive map. They are confirmed sinkholes. So that means that we have either been out there or we've checked, aerial imagery, or someone before you owned the property has called us up and said, hey, I think I have sinkholes, and we confirmed that they are there. So that's something definitely to look out for. And another thing that's interesting, and I'm glad that you talked to Tyler about the surficial material, is that we don't have any sinkholes on the limestone terrain because it goes into the northwest corner on that hill. It's because we often do not see sinkholes in areas where the drift is thicker than 30 feet. So over there, the drift was getting much thicker, so you shouldn't have to worry about over there. But then another thing that draws my eye is this little area on that southern hill, and I'm glad that Erica pointed that out to me. So yeah, same concerns as that. If you remember the bedrock map, you had the shale 2 over, underlying the sandstone, and since shale is a easier to weather material than sandstone, it often will be removed first, and then because of that, it creates instability in the hill, and that can allow for the sandstone to then slump or slide downhill. So this lumpy area of the hill, as you can look at the northwestern corner of the other hill, it's more smooth, kind of gentler hill. The fact that all of these lumps are here tells me that there has been some sliding and slumping in the past. That doesn't mean it's going to, all fall off at once in the future, but that doesn't mean it's also not going to happen. So it's definitely something you want to be aware of and watch out for, because there's still some more hill kind of in the middle that doesn't have any slumping. So something to be on the lookout for. So because of that, if you can go to the next slide, I'm going to go ahead and rule out the landsliding areas. You probably don't want to build on that big of a hill, just in case. It's a little dangerous there. Just you don't want it to slide anymore. And then that's also going to be costly to have to stabilize your foundation for that. And I'm going to recommend you don't build on sinkholes, though they are well draining, and they are not like Florida. You're not going to be swallowed up in the middle of the night. They still are areas of concern. Do not build on sinkholes. So because of that, I am going to recommend the similar area that Tyler mentioned. It is kind of in that till plain, or on that near that northwestern hill. And then a cool thing about karst areas is that they sometimes also produce springs. And if you're going to be building a house here, you're going to probably want to have a reliable source of water. But sometimes those springs are not as active, or they're only during the wet months. So I'm going to recommend that you talk to a hydrogeologist, Tom, and he's going to be able to help you out with figuring where you can build a water well. Do you even have good water for your property? All of that good stuff.
All right, thank you, Brittany. So Andy, as Brittany mentioned, the next thing you might want to consider is a source of drinking water. So if you don't live in a city or town with its own municipal water, you might get your drinking water from a groundwater well. It might sound counterintuitive, but groundwater is often safer and cleaner than surface water. In many situations, only minimal filtering and no added chemicals are needed to make it safe to drink. Groundwater also has advantages over surface water because it is abundant throughout much of the state, even when miles from surface water.
Currently, about 5.6 million people in Ohio get their drinking water from groundwater. Here at the Geo Survey, we collect and share groundwater data on a few different forms. First, we collect records of all the water wells installed in the lake or in the state. Every time a new water well is drilled, a report must be filed with us. And to the right there on your screen is an example log. These reports include the geology encountered while drilling and some basic groundwater data, including the static water level, which is how deep the water is below the ground, and the sustainable yield of the well, or how abundant groundwater is in that location. In addition to collecting water well logs, the Geo Survey also maintains a network of 141 monitoring wells around the state. And if you tuned in on Tuesday, you saw a discussion about that, or they will be up on YouTube in the link shared in the chat. Let's see. These wells collect groundwater data every hour, providing us with time data to track groundwater changes through the year. And there's an example graph. So on the next slide, I'll show you what we do with that groundwater data. So we make a few different geologic maps. On the top left here, we have the groundwater resources map. Groundwater resources maps show the expected well yield and provide some information about what the geology of the aquifer is. To the right of that is the pollution potential map, also called groundwater vulnerability maps. These maps show how quickly a source of pollution potential can spread to the aquifer. We also provide potentiometric surface maps. These maps show the elevation of the groundwater, so drillers have an idea of how deep they need to drill to find the groundwater. And we have statewide aquifer maps. These maps combine the groundwater resources map information and bedrock and surficial geology maps to tell us what the geologic formation of the groundwater is coming from and how productive that formation is. The maps that we will look at for your property, Andy, is the groundwater resources maps and the pollution potential maps. So here's an example of what the groundwater resource map looks like for your property. If you remember, the groundwater resources map shows us how much water we can pump out of the subsurface. And this is controlled by the geology. For example, shale aquifer, shown here in purple, is a very poor aquifer. And groundwater yields from shale are typically between 0 and 5 gallons per minute. On the other hand, limestone, shown in yellow, can be a very productive aquifer with yields ranging from 25 to 100 gallons per minute, which is more than adequate for a standard home. On our map here, shale aquifers are purple. They would not be good places to put a water well. Instead, we'd want to stick to the yellow color where limestone is the aquifer and groundwater yields are higher. In the next slide, we'll take a look at the groundwater vulnerability or pollution potential maps. This map shows how easily a pollution source could move from the land surface into the groundwater. Higher pollution potential ratings tell us where pollutant spills are more dangerous. On this map here, the higher pollution potential areas are shown as orange, with less vulnerable areas being shown as the dark blue. Although not as important for home building, pollution potential maps play a large role in deciding where to build new manufacturing facilities and landfills. If we take a look at our pollution potential map, we might want to avoid installing our well in the orange high pollution potential areas. So on the next slide, as I mentioned earlier, the Geo Survey keeps a record of all the water wells in the state. Typically, those logs are submitted by the water well driller in a form that is similar to what is shown here on the left. Now, as geologists, we use these water well logs to interpret what is going on beneath the surface. So if we color our bar diagram, shown there, in with rock formations and depths described in the log, we can get a good sense of what the geology is at the subsurface at that point. We can then check our log by placing it on our cross-section that we talked about earlier. If both are correct, the contacts between the formations should line up. In these water well logs, unless otherwise denoted, the lowest unit is typically the aquifer. So in this log here, the limestone would be the aquifer. So we'll take a look at your property again, Andy, and decide where we want to place our well. I put some potential sites on the map and added water well logs that we might see in that location. We can rule out the 3 locations on the right because they are in shale aquifers. Shale aquifers have low groundwater yield and are not a good source of groundwater. The next 2 wells I've marked as okay have productive aquifers but are in areas of high pollution potential. They shouldn't be ruled out completely, but there are better places to install our well. The final 2 well sites are the best locations to install a groundwater well for our new house. They have productive aquifers in the subsurface and a low pollution potential rating. So with that information, Andy, I'll pass the discussion back to you and you can talk about where you decided to build your house.
I just want to thank Tyler and Erica and Brittany and Tom. You guys gave me so much good information. I was furiously writing notes about all the geology in the area. And then, you know, looking at all that, I kind of put together this little map, just where I might build my house, and just kind of thinking about how I can take all of those different factors and kind of rank a good, average, or bad building locations. And so I think everybody had kind of nice things to say about the northwest corner of the map. It seems like there's good water quality that Tom was talking about from the limestone, or water availability. And it's a good place to build because it'll be kind of easy to dig out, but not too easy where it's too soft of sediment. So the till would probably make for a pretty good foundation for the house. There's not really any hazards to worry about. So it sounds like kind of the best place to build a house. But then there's some other areas that are kind of gray areas to kind of just bad areas. And so I definitely don't want to build my house right next to the river. Like Tyler said, that can be a really bad flooding risk. And then even in this area, in the marshy area, I might be able to build kind of outside of the floodplain, but I would have to probably pay a lot more money to shore up the foundation and make sure it was strong. So that's probably going to be ruling out. And then these sinkholes here, I definitely don't want to build in those sinkholes. I think Brittany gave me some good advice there. Along with this kind of belt through here where that shale is, and that could be pretty bad for kind of landslides. At the top of the hill, it's probably not as good because that can come down too with the landslides. But it might work depending on how stable the land is. Maybe we could do further studies to see how stable that slope is. But overall, I think what I'm going to do is I'm going to build the house in that northwest corner. And so that's kind of where it's going to go. I thank you guys for giving me that geologic information, and thank you to the viewers for listening to our kind of talk about geologic maps. Hopefully you guys learned about how important geologic maps can be and how they can guide some of our decisions when we're planning construction or any kinds of city planning and things like that. So at this point, if there's any questions for any of the geologists, we can field those now, but thank you.
All right, thanks guys. Let's just hang on 1 second. If anybody has any questions, throw them in the Q&A box and we can relay them. Do you guys have anything you want to add while we just give people a couple minutes to type something up?
Through their descendants and fossils left behind, their legacy lives on.
No, nothing on my end.
Stephanie, I just want to remind everybody that Earth Science Week does continue throughout today and tomorrow. Even though this is our final webinar, there are a number of activities that people can still do to celebrate Earth Science Week. And I'm going to post in the chat a link to the Ohio Geological Survey's Earth Science Week website, where you can get some more information about other things you can do to explore the state's geology and get educated about scenic features, geohazards, and all sorts of other things.
Okay, and we do have the links to our previous webinars up in there too. We do have a question here. What other types of water concerns can geologic maps answer?
Why don't we have our water expert Tom answer that one?
Alrighty.
All right, so as we mentioned, the big issue is water quantity, so how much water you have available. So you can look at the rock types, will give you a good idea. So as I mentioned, shales are typically not a good source of groundwater, so they tend to not have a lot of pore space, which is where the groundwater is actually contained. So there isn't a lot of groundwater there, and it's hard to get the groundwater out of it. On the other hand, you've got limestone. Limestone is typically one of the best aquifers in the area or in the state. But you can have other issues where you have karst features, like Brittany mentioned, and solution features on the inside the rock, where it actually dissolves out and makes large caverns. You can actually have groundwater quality issues with that, where you can change the chemistry of the groundwater. And but that's more of the EPA handles kind of the groundwater quality more than we do. We just look at the quantity mostly.
Okay, we've got one more right now. What would I look for to see if I have landslides?
Landslides, it just depends on the kind of bedrock exposed, especially if you have the, the less resistant material like shale underneath, and a harder, more condensed rock over top. We don't currently have like actual interactive maps of the landslides. I know that ODOT does keep a very good tally on different landslides that affect roads particularly. So you can kind of use that to trace what parts of the state might have a bigger issue with that. It's really going to be kind of in the unglaciated portions of Ohio that you have the potential for landslides because of all the bedrock exposed.
Okay, and we did have one other question, but it looks like Chuck actually answered it in the Q&A for the best way to find geologic maps where I live. And there are some links there. There are a lot of good resources in the Q&A, and thank you guys. That was really helpful. And hopefully we don't have a webinar tomorrow, so that's it for us. Again, check the chat for the links, and thank you all for tuning in.
Thank you.